All right, so today we're going to look at vectors and their dot products. Vectors are essentially review for this course, but I'm finding that more and more that I teach this that people really benefit from a review of it because you don't really see vectors a whole lot until now, and we're going to be using them a lot in this class. So I prefer to go over it than for you to suffer through not knowing what it is, what vectors are, and I think everybody knows what a vector is in this class already, but really to understand them very well, it kind of takes a lot of work. And to be honest, I didn't understand them fully in Cal 3 when I got to it. So let's just talk about, so what is a vector? So what is a vector? All right, so a vector is a directed line segment. It's a directed line segment. All right, and so essentially you just draw an initial point and you draw an arrow and you got your vector. You have your initial point and you have a terminal point at the end. It stops, right? It's a segment, so it stops. So you have a terminal point here. Okay, now a vector can move anywhere in the plane you want, and this was always the thing that kind of got me. I was like, what do you mean it can move anywhere you want? Well, it's used for forces, to describe forces, because a force, say you have a table. Ooh, that looks like a pie. A table, and you apply a force to it. Well, the force has a direction and a magnitude. So if someone applies more force in the same exact direction, the vector gets longer. Okay, that's how we do it. All right, if they apply less force, then the vector would get smaller, so less force here. Okay, so it'll become more apparent later why it doesn't matter where the vector is in the plane. But so that's what you got so far. Okay, so anyway, so let's draw this vector, draw vector v. So a vector v starts at the origin, we call it a position vector. All right, if it doesn't start at the origin, okay, then we can manipulate the points so that the vector moves to the origin. Uh, its initial point is at the origin. That's kind of what I mean. So if you look, for example, at this vector here, let's say it starts at P and P is at, I don't know, what is that? Maybe 4 comma negative 2. And then it ends at Q. And maybe Q is, I don't know what that looks like, maybe 10 comma negative 3. So the vector that you get out of this will be vector v. Oops, get rid of that. You get vector v is pq, starts at p, ends at q. And so what you do is you erase a lot. You do the last point. So the last point is 10 minus 4, and then negative 3 minus a negative 2, negative 3 minus a negative 2. All right, so it's 6 comma, and this is negative 1. So if you go back to this here, if you draw 6 negative 1 over 6 down negative 1, you should get the same vector as PQ. Let's do a different color. Similar, okay? If this was to scale, it's never to scale in my class, but if this were to scale, you would see that this green vector is the same as this blue vector. So I invite you to practice this with at least one, but do it to scale, okay, so that you understand it, so that you really get this idea. All right, so you're convinced, in other words, but make it to scale. All right, so you might want to practice maybe, I don't know, they probably have this in the book, in the homework, maybe that one, or maybe 58. 58 is a good one too. All right, so anyway, so if you have any vector in the plane, like this PQ, you can make it so that you can manipulate it so that it starts at the origin. And a lot of times you may have many forces acting on an object, okay? You might have many forces acting on an object, you know, and in order to determine what the total force is, you put them all at the origin. All right. So that's the motivation behind that. All right. So what's coming up? Let's see. We need to talk about the magnitude of a vector. All right. So the magnitude of a vector, magnitude, is its length. So in a geometric sense, it's equivalent to its length. Equivalent to its length. All right. So if you're talking about a force, it's how much force is applied. Okay. So if you have a vector v, and the vector v is denoted by v1 comma v2. Now, if it's in this form, this implies this is a position vector, and this implies that it starts at 0 and it ends at v1 comma v2. So, for example, if you have v is, that's not a v, that's a u. If you have v equals, let's say 3 comma negative 4. All right. So if you draw that in a plane, 1, 2, 3, down 1, 2, 3, and then 4. Then when you draw this vector, there we go. When you draw this vector 3, negative 4, it ends at the point 3 comma negative 4. Okay, but as a vector, we're going to write it with the greater than and equal, or greater than and less than signs. All right. So that's that. So let's go back to what the magnitude of a vector is. All right. Well, I love this ink to shape business. So the magnitude of a vector, so the length, if you look at this one here, the length of this vector, this is a good example of one actually. It's 3 here, and then this length here is 4. So the length of this vector will just be, the Pythagorean theorem gives you c squared equals a squared plus b squared. And then to find c, you take the square root of that. So this would be 9 plus 16. So in this case, it'd be 5. All right, so this is b5. So the way we write that for this problem here, this one here, is that the magnitude of v, we're going to use absolute value bars, 2 of them for vectors, and that would be 5. Now the reason why we use absolute value bars, they kind of look like absolute value bars, but they're double, is because the absolute value is the distance from the origin. So in previous math courses, when you said, here's 0, what is the absolute value of, I don't know, let's say this is negative 3. The absolute value of negative 3 is 3 because there are 3 units from the origin. And then if you look at this vector here, all right, this vector is 5 units from the origin, going kind of like in a radial way. All right, so that's the motivation behind why we use that symbol there. All right, so this looks like a bunch of chicken scratch, doesn't it? So let me get rid of some of this. All right, so let me give you a formal definition of the magnitude of the vector. So the magnitude of v is equal to the square root of v1 squared plus v2 squared. Okay, if v is v1 comma v2. Now this should be in this formulas up here. Let's see here. Position vector, unit vector, dot product. No, it's not. Oh, okay, well, you need to know it anyway. Because if you notice, it pops up everywhere. All right, so you need to know it. So just get to know it. And that's all there is to it. So let's actually do an example of this. So if v is I don't know, 2 comma 7. All right. So this means that the magnitude of v is square root of 2 squared plus 7 squared, which is the square root of 4 plus 49, which is the square root of 53. Okay, now if you're in WebAssign only takes exact answers unless it asks for a decimal equivalent. So square root of 53 would be your answer in WebAssign. Okay, so be careful. Now, one thing here, a lot of times I'll be writing v magnitude of v like this with only one pair of up and down bars. It's kind of bad form. It's not bad form in a sense, it's just laziness. But you'll see this, so just know that in the context it's the magnitude. Okay. Now, always write that line above your vector, okay, to tell the reader that it's a vector. All right, it's very important. All right, so now let's talk about what a unit vector is, because I saw that up in the formulas there. All right, so a unit vector is a vector that's in the same direction as v, but it points, it's in the same direction as v, but it's divided by the length of v. So if I say the vector u sub v, that'll be v divided by its length. All right, so here we go. Let me explain why this is true. So let's just do an example with it. All right, so if we go back to that v equals 3, 4 example, or let's say 3, negative 4, we saw that the magnitude there was 5. So if you take v and now you divide it by its magnitude, you get 3/5, comma, negative 4/5. All right. So now when you take whenever you find the magnitude of this one, okay, so this is now u, and I'm going to write u sub v. You don't see this u sub v, you don't see the sub v much, but I like to write it because it says u is associated to v. So now let's find the magnitude of u. So that will be the square root of 3/5 quantity squared plus negative 4/5 quantity squared. It's this vector here. Okay, we're using that vector. So 3/5 squared is 9/25, and negative 4/5 squared is 16/25, which is the square root of 25 over 25, which is 1. And so it's a unit vector. So a unit vector has a length of 1. Okay, so whatever you get for this here is always 1. Okay, the length is always 1. The length is 1. It's not 1. The length is 1. Okay, so length is 1. All right. So with that said, the unit vector, why do you use it? Well, because a lot of times we just want to know the direction of the vector. So suppose this is u, this is v. A lot of times we want to know the direction of the vector, but not the length. And so what we'll do instead is we'll use u instead. So here's v, and then u will be running along it with a length of just 1. Okay, and this will become more apparent in subsequent sections. All right, so that's the unit vector. So we got that down. So how do you add two vectors together? Well, you just add them point-wise. So if you want to add two vectors that are position vectors, you can just add them point-wise. Let me see if I can go further down here. All right, so if you want to add two vectors, you just add them point-wise. So adding vectors. Now the geometric version of adding, you're going to look at that in the book. Okay, so if you want to add two vectors, suppose u is 3, negative 2, and v is negative 1, 1. Then u plus v is 3 minus 1, negative 2 plus 1, and that would be 2, negative 1. Okay, so that's the answer. All right, so that's adding vectors. And then you can add their magnitudes and things like that. Okay, I'll let you work on that. Now I want to get to some meteor type problems, some problems that are a little harder. A lot of times you see a degree associated to a vector, So let's talk about that. If you draw the xy plane, if you have a vector v coming out of it, like that, coming out of the origin, then the angle associated, let's call it angle theta, the angle associated to it you can find using the components of the vector. So let's suppose that v is composed of v1 and v2. Well, if you look, tangent of theta, tangent of theta is just v2 over v1. It's the opposite over the adjacent. So you can get the angle of the vector very simply by doing that. So when you look at problems like this one here, like let's look at 70, find the vector v in the xy plane with magnitude 5 if the angle between v and I is 150. Okay, we're going to talk about this I. So what is I? Well, for now, let's just say, instead of I, let's just say the x-axis, and then I'll come back to I in a second. So we're going to find the vector v in the plane, in the xy plane with magnitude 5 if the angle between v and the x-axis is 150. Okay, so let's look at that. So what we have here is 150 is 30 degrees away from the negative x-axis. So here. So v is here. All right, so 150 is here. 150 is there. And so the magnitude here is 5. So the length of the vector v is 5. So the tangent doesn't really come into play here as much as cosine and sine. So one thing I want to teach you here is that v, let's talk about this for a second. V is the magnitude of v times cosine of theta, comma, the sine of theta. All right. So I want you just to look at this formula for a second. Let's work with it with this problem, and then I'll derive it for you. All right. So in this problem we have v is 5 because that's the magnitude of v. So the magnitude of 5, and then we have cosine of 150, comma, sine of 150. All right. So the cosine of 150 is the negative cosine of 30 using reference angles, and this is the sine of 30 using reference angles. Go back to trig for that if you want, or just ask me in office hours or the question and answer session. So this is 5 times cosine of 30 is root 3 over 2, and the sine of 30 is 1/2. So your vector is negative 5 root 3 over 2, comma, 5/2. And that's your vector. And that vector will end at the point negative 5 root 3 over 2, comma, 5/2. That's the point. So if you go back to this problem here, the actual little point here that v ends at is this negative 5 square root of 3 over 2, comma, 5/2. Okay, and so that's what's going on here. So now let's talk about what this formula, where this formula comes from. So what the heck is that? So let me go a little further over here. So why is this true? Why? Well, let's see. All right, so let's just draw a vector in the plane. Say it looks like this. Here's v. And v is composed of 2 other vectors. If we add these 2 vectors together, this vector here and here, if you add vector here, this is v2, let's say this is v2 and then this is v1. Okay, if you take v1 plus v2 using geometry, you're going to get v, because it forms a rectangle. All right. So with that said, if v is composed of these 2 vectors, if you add these 2 vectors and you get v, then the length of v1 is here and the length of v2 is here. And so we have v equals v1 comma v2. Now v1, if you look at the angle theta here, the cosine of v1 is, okay, so I can move v2 over. Get rid of this. Get rid of this. This length here is v2. Okay, so it looks like the cosine of theta is v2. It's no, cosine is adjacent over hypotenuse. So that's v1 over the hypotenuse is the length of v. It's not v. V is a vector. The length of v is the hypotenuse. Okay, so it's the adjacent over the hypotenuse. Okay, so then what this says then is that v1 is the magnitude of v times the cosine of theta. Now similarly, v2 is the magnitude of v times the sine of theta. Because if you take the sine here, sine of theta is going to be the opposite, v2, over the hypotenuse, which is the length of v. All right? And then so you get magnitude of v times the sine of theta is v2. All right, so with that said, we can come down here, use these two together. We knew that v was v1 comma v2, so that's just magnitude of v times the cosine of theta. Just getting that from here. Just getting that from here. And then comma magnitude of v times the sine of theta. And I'm getting that from here. Okay? Alright, so now I want to take out the magnitude of v, and I'm just left with cosine theta, sine theta. And we're going to really use this a lot, actually, so it's good to know it. Alright, so v is also known as the magnitude of v times cosine theta, sine theta in the brackets there. So let's see if that's a formula over here that you need to know. Let's see. Oh, they don't have it in here, but you need to know it. So put it in there. So magnitude of v, v is magnitude of v v is magnitude of v cosine theta sine theta, like that. Okay, so know those, please. All right, anyway, so let's see what we're getting to here. Now, one thing I want to show you is that even though we've dealt with vectors that are just in 2 space, vectors are in 3 space as well, obviously, and everything just comes straight over. All right, everything we learned just comes straight over. Now, I want to look at this I and j business here. Okay, so what are those? Well, you might have learned vectors that way, actually, it's great and all. I don't use I and j much, but you do need to know it. So it looks like we have I and j to deal with. So we're going to make a definition. I with a little hat on it. Okay, the I vector is 1, 0. It's the vector 1, 0. J is the vector 0, 1. Now let's go ahead and put a third one on there. 1, 0, 0. We're in 3 space now. J is 0, 1, 0. And then K, we're just defining these as this, okay? 0, 0, 1. Alright? So if you want to take a vector, right, suppose your vector is 1, negative 2, 5. So you can write this as 1, 0, 0 plus 0, negative 2, 0 plus 0, 0, 5. Now, with that said, you can always pull a number out. There's nothing to pull out of the first one, but you can pull out a negative 2 out of the second one. 0, 1, 0. All right. No problem right in that last bracket. Plus, and then 5, 0, 0, 1. And then the way I've defined these vectors here, I can pull them down there. Okay, so what we get then is I minus 2, this here is j, and then plus 5, and then k, like that. So that's the vector, let's call it, yeah, we called it v, so v. So these are equivalent here. This here is equivalent to this, okay? And physicists like to use this, okay? So physics likes to use this a lot. I don't really like it much. In fact, most math classes I saw beyond this level didn't use IJK much. They used more the bracket level, but it's up to you. If you learned it with IJ and K, great. You can use it. It doesn't bother me. All right, whatever makes you happy and whatever helps you understand the material better. All right. So that's what all this is about here. It says find the dot product. It uses all this IJK stuff, and then it says use the vectors here and here to find each expression, cross product and plus and all this. We'll get to dot product and cross product in a second. I'm going to let you do the distance, find the distance formula. That's straight out of algebra. So what is this dot product? The cross product is here. The dot product is this guy right here, this little dot. So let's walk into that. So that's 12.2 now. I'm lost. Where am I on this page? Jeez. All right, so let's see. So let's talk about the dot product. Okay, so definition. If U is U1, U2, U3, so we're in 3 space, a 3-dimensional vector, and V is V1, comma V2, comma V3, then the dot product is just the product of the corresponding points. All right, so then U dotted with V is just U1 V1 plus U2 times V2 plus U3 times V3. So this is a number. This is going to be a number usually, okay? If you have these are numbers, and these are numbers, and this is a number, okay? The cross product is going to give us a vector. That's something different, all right? They're not related. They just have the same word product in their name, okay? All right, so let's do an example. I'll use a different color for the example. Let's suppose that U is -1, and then V is, which I had some actual students listening in. I could get some suggestions. Let me think -5 and then -3 here. Okay, like that. All right, so U dotted with V is going to be 0, 0 times 1 is 0, plus 2 times -5, plus this -1 times -3. -3 here. So then we got, what do we got here? 0 minus 10 plus 3 is -7. Okay, so -7 is our dot product. All right, so where does this come in? Well, if you look, there's a formula that we're going to use for the dot product, and it is this one right here. All right, so the cosine of theta is going to be angle between the two vectors. Okay, cosine of theta is the dot product of the two vectors over the length of the first vector times the length of the second vector. So let's do a problem like that. Actually, we can do this one here, the one we just did. So let's find the angle between the two vectors. So let's find U and V. So U and V. All right. So cosine of theta is going to be the dot product, which we found to be -7. So -7 over the length of U. The length of U is the square root of 5. And the length of V is the square root of, what's that, 1 plus 25 plus 9 is 35. All right, so now, apparently, so this number here, let's go ahead and get this number on a calculator. All right, it is about -0.5291502. 0262, something like that. So that's the cosine of theta. So then theta will be the inverse cosine of this number. Let's just put this number here. This number goes there. And so when you do inverse cosine on your calculator, you get 2.13 degrees. So that's in radians. My calculator's in radians. So I'm getting about 122 degrees. Okay, so that's the angle between those two, 122 degrees. Let's see if that makes sense. Oh wait, there's the 3-dimensional ones. No, these are hard. These guys are really hard to determine what the angle is between them. Just looking at them, or to verifying that this is that. That's that 122 is the angle. But I would definitely try this in 2D and see what you get. See how far you get with that. All right, so that's an example of that. This formula here, the one we've been using, cosine of theta, is u dot v over the length of u times the length of v. This comes from the law of cosines from trig. Okay, so if you want to see the derivation of it, the derivation uses the law of cosines. It uses it. So if you want to see the derivation is in the book. All right. So what do we got here? It's cross product there, dot product. All right. So another kind of problem. Oh, yeah. Let's get to an example of where one of the properties. Okay. So let me erase some of this. We can leave it. I'll just move over. So one of the properties, I went ahead and erased it. One of the properties of the dot product property is that u dotted with v is 0 if and only if u is perpendicular to v. All right, this is very, very useful. All right, and the reason why is because if you look at the formula, cosine of theta is u dot v over length of u, length of v. If this is equal to 0, then only the numerator is 0. Okay, so if you have a fraction equal to 0, this implies then that only the numerator is 0. Only a is 0 in this case. Okay, so if this is the case, if u dot v is 0, okay, so if this formula here is 0, that means that cosine of theta is 0. So cosine of theta is 0 means that theta is either 90 degrees or 270 degrees. Okay, remember what cosine looks like. There's cosine. There's cosine. This is 90 here, and this is 270 here. Or if you want, pi over 2 and 3 pi over 2. All right. So it's 0 either way. Well, if it's 90 degrees, okay, if two vectors are 90 degrees apart, or if they're 270 degrees apart, they're perpendicular either way. All right. So if the cosine of theta is 0, then they're perpendicular. And if the dot product is 0, then the dot product being 0 means that the cosine of theta is 0. And so this is an if and only if statement. Okay. So if you ever want to find out if two vectors are perpendicular, or what in this case we call orthogonal, so perpendicular in vector words is orthogonal. We use orthogonal, and this is because we use a different word because vector theory was developed in different parts of the world at the same time, and so some people use orthogonal and some people use perpendicular. Now they're just interchangeable words. All right, so that's that. And then there's one kind of problem that's really important. It's using the projection of the two vectors. All right, so let me pull it over here. So the projection, okay, of let's say u onto v is given by this. So say you do PROJ u onto v like this, or let's say v onto u. Let me do v onto u because that's u onto v. No, it doesn't matter. U onto v. That's fine. So that's going to be u dot v over the length of v squared times v. Now sometimes they write it like this: u dot v over the length of v times v over the length of v. So this in front here, this is a scalar, or if you want, that's another word in vector theory for number. And then here, this piece is just a unit vector. It's the unit vector in the direction of v that has length 1. Okay, so they sometimes call this the component of u onto v. Okay, so it's the scalar projection of u onto v. So, so what is all this? Well, it's essentially just a piece of U that's on the shadow, that's shadowing on V in a way, if I can like really piss people off and say it that way. So if you have, for example, if you have U here and you have V down here, then the shadow of U onto V, the perpendicular projection of U onto V, will be just this piece right here. Okay, so this is the projection of U onto V. Okay, this number in front, the component, that is the length. Okay, that's the length. And this here, let me do a different color for that. This part here, that unit vector piece, that's just maybe a length of 1 along it. Let's assume this is length 1 here. Okay, so that's one example of where unit vectors come in handy. So anyway, let's do an example of this. I would like you to memorize this formula. Please memorize this. And let's do an example. Let's see. Maybe 104 works. So it's -1, 2, and 3, -1. So U is -1, 2, and V is 3, -1. I don't know. Did I write that down right? Let me see. -1, 2, and 3, -1. Yeah, that's it. Okay, so here we go. Projection of U onto V is, so it's going to be U dot V. So it's going to be that -1. Well, yeah, so -1 times 3 plus 2 times -1 over, now the length of V squared. So the length of V, let's take V over here. The length of V is, the magnitude of V, in other words, is the square root of 9 plus 1, which is the square root of 10. So we're going to square that, right? We're going to square it. It's squared. So now that becomes a 10. And so we get, now we're going to multiply times V itself. This looks like a J. It's a V. So that's 3, -1. All right, so what is all this mess? So this is -3 minus 2 is -5 over 10. 3 comma -1. So that would be -1/2 times 3 -1, which is -3/2 comma 1/2. So now if we graph all this together, all right, let me see how this looks. Let me go further over. If we graph all this together, let me pop in a view here. I think view rule lines. There we go. Ooh, that's bad. All right, -1. These are not fun. These tablets aren't fun to draw on sometimes. What I've noticed. There we go. So let's pull U over. So U is -1, 2. So it's -1 up 2. Maybe that's right there. So that ends here. And then, is that right there? Yeah, -1, 2. And now V is 3, -1. So I'm going to go over 3. 1, 2, 3. And maybe this is -1 there. So now V is over here. Okay, now the projection of U onto V. So if you notice, U is behind V when you, the shadow of it. So if I project V back, then U projected onto V is going to be back here. So it's going to be this vector here. And so that's the projection of u onto v. All right, and so that's kind of what we got, actually. If you look, maybe this is -3/2, and maybe this is 1/2 here. Okay, it's off scale, but that's kind of how, not to scale. It's kind of how it goes. All right, and that's the projection. So I invite you to do some more problems like that. Now, one problem that is like this is, so wait, we haven't finished this yet. So it says decompose V into two vectors, one parallel to W and one orthogonal to W. Okay, so I've mislabeled this. Let me call this U, and let me call this V. Okay, so 1V. So we're going to decompose W. This is going to be V into two vectors, one parallel to W. So now this is going to be V. This is going to be V, and this is going to be U. It's all the same. This is probably how I would write it on the test anyway. Okay, so let me write down that. Okay, so the directions are decompose U into two vectors. Let's call them U1 and U2, where U1 is parallel to V and U2 is perpendicular or orthogonal to V. Okay, so we already have this one here. We have this one here. It's the projection. So if you look, U, just use this blue vector here, okay? Use the blue vector here. It's composed of two vectors, one parallel to V, which is the projection vector here, right? This is projection vector, and another one perpendicular to it. So let me draw that in green. Perpendicular. Now remember, whenever you have a rectangle of vectors, then the diagonal is going to be the addition of the outer ones. So the red one we're going to call U1. Already got that one. And the green one we're going to call U2. Okay. So I tell you what, let me redraw this so that it makes more sense. So what we had there was this situation. I'm going to assume U looks like this. Here's U. And then the projection, let me make this a little more up. The projection was in red, like that. And now a vector perpendicular to that is in green here. Okay, so this is U2, and this one's U1. And then we have U there. So if you remember from some theory before, U1 plus U2 is U, because they form a rectangle. There's a rectangle going on here. Doesn't look like it, but there is. Okay, so this guy here is just a projection. So we got that as, well, I'll tell you what, before I show you what that is, we need to find U2 now. So the directions are this. So decompose U into two vectors, U1 and U2, where U1 is parallel to V. Now remember, V was, where was V? V was down here. So one's parallel to V. So we got U1 is that one. So that's the projection. And then U2 had to be perpendicular to V. And so that's this green vector here. Okay. That's this one. So if you want, we need to find U2. We have the expression for U. Okay. So U was negative 1, 2. And we have the expression for u1. That was, what do we find out the projection to be? Negative 3 halves, 1 half. So that was negative 3 halves, 1 half. So what we can do to solve for u2 is just move u1 over. So u2 is u minus u1. And so we just take these answers that we got and subtract them. So u is negative 1, 2, minus u1 is negative 3 halves, 1 half. So this is, oh gosh, don't ask me to do complex math. 2 minus 1 half. And so this is 1 half. You watch, I'm going to get this wrong because I was flip about it. There it is. This is V2. This is U2. Sorry, U2. And there you have it. So you have U1 and U2. And those are two vectors that form U out of that. Okay? So that's how you do that kind of problem. So I would invite you to look at problems like this one right here and this one right here, because this is kind of where the rubber hits the road. I wouldn't worry too much about the work examples. Remind me, we need to go over the area of a parallelogram as well. Well, I'll tell you what, I'm going to let you do that. That's just a formula. Hopefully it's in here. Yeah, it's right here. Oh, wait, it's cross product. So we'll get to that next time. Okay, so that finishes up the lecture on vectors and dot product. Okay, so hope you enjoyed it.